So different chemical species have different magnetic properties. So at the very beginning we talked about the density, and this RW means relative to water. So if you look at cerebral spinal fluid, it's mostly water. So we know that CSF is mostly water, so when you look at the proton density of CSF, it's basically 1 because it's 1 relative to water. We know that gray matter, white matter, and fat have slightly lower densities, both in terms of just their physical properties, but also that means that they have fewer protons per unit volume. And so if you look at the T1 and T2 values of these different chemical species, you can see that CSF has a really long T1 and a really long T2 compared to these other tissues. Okay? Now, these values are actually dependent on the magnetic field strength. And the way you can think about that is, we know that after we apply these pulses, we get a slow regrowth along the Z direction of that M0 vector. Well, at higher field strength, we know that that M0 vector is actually larger, which means that it's going to take a little bit longer to actually get fully back into the longitudinal direction. So if you just compare this slide with the previous slide, by the way, these small subscripts are the references that I used to create them, which I will give on the next slide, and so you can have them for later if you want. So as we increase the magnetic field, the proton density relative to water remains the same. We're not adding hydrogen protons magically to this tissue. All that we're doing is we're increasing the amount of time it takes to regrow that Z magnetization, and we're also actually, in some cases, decreasing the amount of time it takes for it to dephase, because the vectors are actually fatter. So they interact a little bit more when they dephase, okay? And so these are the references. So all of these presentations will be made available after the fact, so don't worry if you can't copy down all of these references in time. And also, if you want them, you can just email me. All right, so that brings us to the end of the first half, where we talk about relaxation for part 2. And so now what we want to do is we want to take those relaxation properties, both the transverse dephasing relaxation and also this longitudinal recovery, and we want to use it to manipulate some images. Okay? And so we're going to start off talking about just some philosophical ideas about image contrast and what it actually means. Okay? So can anybody tell me which center circle is darker in these two images? Yeah, of course you've probably seen this demonstration before. They're actually the same, and just to prove it, if we slide this over, you can see that the center circles actually have the same image intensity, okay? But the one on the far right seems more conspicuous because there's better contrast between the center circle and the ring, okay? And an example of this is the difference between gray matter and white matter. And what we're going to do is we're going to manipulate these T1 and T2 properties to actually tease out some of this image contrast, okay? All right, so as I mentioned the color scheme before, if I'm going to change it at all on the slide, I'm going to explicitly state it. And so here we're looking at white matter is in green, gray matter is in red, and cerebral spinal fluid is in blue. Okay? And so we know that the M0, in addition to being proportional to B0, is also proportional to the proton density relative to water. Okay? And so this is the behavior following our Bloch equation that we just showed as a function of time after a 90-degree pulse for these 3 tissues. Okay? So imagine there's 3 different voxels. Each voxel, one voxel contains gray matter, one voxel contains white matter, one voxel contains cerebral spinal fluid. Now, we know from what we just talked about, cerebral spinal fluid has a very, very long T1 recovery, which means that it's following this much more gradual curve back to this value of 1. Now, I want to point out here that the M0 that I'm talking about here is, remember, is relative to water. So the proton density relative to water of CSF is 1, and gray matter and white matter are much closer together at 0.6 and 0.69. Okay? Now, we also see what happens in the rotating frame as a function of time as well. Okay, both white matter and gray matter have a very short T2, which means that their spins dephase faster compared to cerebral spinal fluid that has a long T2, which means that its transverse decay is also very slow compared to the other two. Okay? All right, so we're going to try to build our model in our mind towards being able to look at a pulse sequence diagram in either magnetic resonance in medicine or JMRI or some of these combined physics and clinical journals where somebody's introducing a new pulse sequence, let's say, just so you can get an idea of what those diagrams that they're showing actually mean. So this is just one step in that process, okay? So if we look at all of these graphs are plotted as a function of time. So we've got this radio frequency line here. We apply a 90-degree pulse, and now we're looking at the Z magnetization on one graph and the XY transverse or rotating frame plot on this line, okay? And so we're using the same color scheme from the previous slide with white matter, gray matter, and cerebral spinal fluid. So this is just the same graph that I just showed, okay? And so what I want to do is zoom in on this first little section here, okay? So that's all this is just a zoom in of the first few hundred milliseconds of the graph that I just showed. Okay, so you can see in the Z recovery here that they're pretty indistinguishable in terms of just the magnitude of their Z magnetization. But what you can see down here is that we actually have a disparity in how much transverse magnetization is available. Remember, when we apply a 90-degree pulse, we're tipping all of the magnetization for all three chemical species into the transverse plane, okay? And because M0 is proportional to proton density, that's why CSF has a higher value here, because it's got a proton density of 1, whereas these two have a proton density of about 0.6, okay? Now, so as we're building this model, we're going to talk about this concept of echo time throughout the course of this series, okay? But for now, I want you to think of echo time as the time when we click our camera. So basically, we click the shutter and acquire our signal, okay? And so we call this, so in this particular case, we have chosen an echo time or a shutter speed time of this. Okay, and that's the point at which we get our image contrast. Okay, now in the next actual part 3, we're going to talk a little bit more about what an echo actually is. But for now, in your model, just think about it as when you click that camera button to take your picture. Okay. Now, just by changing when we click that shutter, we can manipulate the image contrast. So if we collect an image here, we're going to get a specific type of signal intensity in our image relative to this transverse signal. If we increase it, we're going to get a different contrast. Now, because gray matter and white matter have a shorter T2, they have less signal intensity at this longer echo time. And if we go way out here, with this third echo, the longer of the 3 echoes, now the only chemical species that still has any viable signal left is CSF, because it has a long T2, okay? And so this is the essence of a T2 weighted image. So in a T2 weighted image, a chemical species that has a long T2 is going to be brighter than one that has a shorter T2, okay? And so some of you may have seen T2 weighted images of a brain. The CSF is very bright, and the gray matter and white matter is very dark. All right, now we've already looked at what happens as a function of time if we apply one 90-degree pulse, okay? What happens when we apply a second 90-degree pulse, okay? Now, if we wait long enough and apply that second 90-degree pulse, the curve's not going to look any different. The difference comes when we start applying that second pulse before one of the chemical species has recovered, in this case, cerebral spinal fluid, okay? So here we've taken the same duration and basically chopped it in half. Now, our magnetization, you can see it here, has gone from 1 after the first pulse to something less than 1. And the reason is because we've applied that second 90-degree pulse before the CSF has been able to fully recover, which means that there's not as much available when we apply that next pulse. Okay? Which brings us to this idea of repetition time. So repetition time is the duration between those alpha pulses. Okay? Now, we've already talked about the 3 different things that you can do on the scanner. We've talked about flip angle, we've talked about echo time, and now we're talking about TR. These are 3 parameters that are available on every scanner sequence and console that you can use to manipulate image contrast. Okay? So, what we want to look at is the effects of decreasing this TR. Okay? Or increasing in some cases. Okay? So we've already shown what happens when you apply a second 90-degree pulse. Okay? What happens if we decrease TR even further, and even further, and even further? And so now what you can see down here in the transverse plane is that we're getting less and less CSF contrast when we click our camera, because there's less magnetization being tipped with each of these 90-degree pulses. Okay? So the effect of decreasing TR gives you more T1 contrast ratio weighting. Okay? So your T1 weighted image is an image where the shorter T1 species have a brighter signal because they've been able to recover more before you apply that next pulse. Okay? And so these are just some examples of, this is just an example of a simulated T1 weighted image. Okay, so if we have a very short TR, in this case 4 milliseconds, which is way beyond the 4,300 millisecond T1 recovery of CSF, and in this case we've just got a short echo time of 2 milliseconds, then we get this type of image. And so you can see there's not a complete zero of the CSF. So you can think of the zero as being this air outside the tissue. But you can see that there's much more signal intensity from the gray matter and white matter because they have shorter T1s, so they've had more time to recover. They've reached their thermodynamic equilibrium magnetization before we apply that next alpha pulse. Okay? Now, some of you may be familiar with MR contrast agents. So MR contrast agents typically contain gadolinium ions. Okay, so just to refresh your memory about first year chemistry. So gadolinium has 64 protons, 64 electrons, greater than 90 neutrons. And the important thing to point out is that gadolinium is actually a heavy metal, so in its ionic form, it's actually extremely toxic for the body. And so the way we make it biocompatible is by applying a chelation process. So we have these chelation molecules that basically render the toxic gadolinium ions biocompatible. And so what that does, what the effect of injecting these chelation molecules into the bloodstream is, it reduces the T1 time of the blood so that it's much faster, which means that if we're applying a T1 weighted image, the blood vessels are going to appear brighter. Okay? Now, the next thing I want to talk about is further manipulation of the T1 relaxation that we've already alluded to, and that's inversion recovery. Okay, so now we're instead of applying a 90-degree pulse, we're applying a 180-degree pulse. Okay, so now all of our M0 is being tipped into the negative Z direction. Okay, remember our proton density is weighted based on the number of protons available. So because CSF has a proton density of 1, when we measure it relative to its own M0, we get a magnetization of -1, and we get this slow recovery along here based on this T1 time. Okay? Gray matter and white matter have similar T1s, and they look something like this. So they've fully recovered even after a 180-degree pulse by around here. Now, what we do in inversion recovery imaging is we try to time the application of a 90-degree pulse after one of these 180-degree pulses. So if we time it exactly right, we can apply our 90-degree pulse when CSF is at its MZ equals 0 point. Remember, if we have a perfect 180-degree pulse, how much transverse magnetization do we have? 0. And if we time the application of our 90-degree pulse right, we also have 0 Z magnetization. Okay, so the essence of inversion recovery is timing the application the timing between the initial 180-degree pulse and the second 90-degree pulse at just the right time to basically null all of the magnetization from a particular chemical species. Okay? And so the way this looks in our modified pulse sequence vector diagram, so we have a 180-degree pulse, and then we have some inversion recovery time, which we call TI, and then we apply a 90-degree pulse, okay? And so when we look at the transverse magnetization as a function of time, you can see that CSF is always 0 because after the 90-degree pulse or 180-degree pulse, there's nothing. We've timed that 90-degree pulse to go through the 0 point of the MZ magnetization, which means there's also nothing available for the 90-degree pulse. Okay, so now we've got more image contrast between gray matter and white matter, and we should have basically 0 signal at all from the CSF. Now, that inversion time is critical. Like you want to pick as close to the null point as possible, and this is why. So suppose we apply our 180-degree pulse. We know that we're going to have some recovery. If we don't wait till we're in that sweet spot, what happens when we apply that 90-degree pulse is we get non-zero transverse magnetization, which is going to present itself as some sort of bright non-zero signal intensity in our image. Okay, so it's very important. So if we adjust this, if we apply our 90-degree pulse before we're at the null point, we get a different T1 recovery curve. And so if we apply it at just the right time.
10 minutes remaining in this video conference session.
Okay, thank you. But if we look at the behavior in the transverse plane of that same phenomenon, then we get some sort of non-zero magnetization, which is going to decay away according to our T2 that we just talked about earlier. Okay, and then we're going to get this regrowth along the Z direction. Okay, and so inversion recovery is a very good method for suppressing CSF in your images. Okay, and so this is the same brain simulation that I just showed, but choosing an inversion time that is exactly tuned to when CSF crosses that 0 plane, and you can see that we still don't have a lot of image contrast between gray matter and white matter in this particular image because their T1 and T2 properties are fairly similar, but we've completely nulled the CSF. Okay, and so this is just a comparison between applying short TRs versus timing your inversion the same way. So you can see there's the actual contrast between gray and white matter is very similar between these two images because our echo time is the same, but you can see the drastic difference in the CSF. Okay, and so this is the basis for MP-RAGE imaging, which a lot of you may be familiar with in your anatomical images. And so basically, instead of applying just one 90-degree pulse, you basically apply a bunch of 7-degree or some small flip angle at or around the null point of the CSF, and that's just basically to try to speed up the actual acquisition. So if I just zoom in on the center part, so basically there's very little CSF signal compared to the gray matter and white matter. And so this is just an example of an MP-RAGE T1 weighted image. So MP-RAGE is just T1 weighting with an inversion, okay? Okay, so we talked about what happens when we have a short TR and a short TE. What happens if we have a long TR and a long TE? Well, if we have a long TR, we know we're going to get full recovery of all of our species, including CSF. And if we have a long TE, the only signals that are going to be available to us are CSF, because the transverse magnetization of gray matter and white matter will have decayed away, and all that's left in the transverse plane is this CSF signal. And so that's how we create T2 weighted images. So a long TR to minimize any effects of the longitudinal relaxation differences, and a long T2 so that we can get as much image contrast out of that T2 property as we possibly can. Okay? Okay, and now the last scenario is a long TR and a short TE. Well, again, long TR minimizes the effects of longitudinal relaxation. A short TE minimizes the effects of T2 decay, and this is how we actually get a proton density weighted image. So by choosing a long TR and a short TE, we've minimized the effects of both the longitudinal and transverse relaxation. So the image, the pixels that we're seeing in our image are weighted based on the proton density. Okay? And so these are just the three images side by side. So to get, without doing any sort of inversion recovery, if we use a short TR and a short TE, we get a T1 weighted image. If we use a long TR and a long TE, we get a T2 weighted image. And then if we apply a long TR and a short TE, we get this proton density weighted image. Okay? And so for those of you that are interested, these are just the parameters that I used for the simulations in that particular spot. And so that brings us to the end of part 2. So the first part, we talked about this concept of relaxation. We talked about the Bloch equation. Remember the don't call me Bloch equation. So we have this longitudinal regrowth along the Z direction that is always going to bring us back to our M0. We have this transverse dephasing, and remember, this is in the rotating frame of reference, and we still have that oscillation that we use to detect our MR signal. We talked about the concept of TR, so how often are we applying these alpha pulses, and that's going to affect how much T1 recovery we have. And we also talked about this echo time, which is when we click the shutter on our camera and how that affects our image contrast at the time of imaging. And then we talked about the different types of images that we can create just by manipulating TR and TE, and whether or not we're using an inversion recovery. Okay? All right. So next time, we're going to get into gradients, and we're going to talk a little bit more about this idea of echoes. So it's not as simple as just clicking the shutter on your camera, and we'll explain it a little bit more in detail next time. But it's just to give you a concept of how echo time actually affects the image contrast. Okay, and then this idea of gradients. Okay, so. Gradients are always going to be this pinkish purple color as well from our color scheme. And with that, I'd like to acknowledge the M&I Atlas that I was using for these simulations. And with that, that's all we have. So.